Good evening, friends. So up till now we have been discuss about the various dimensionless number like Nusselt number, and now as per the correction factor for heating or cooling concern, it is very essential. Generally, when hot or cold fluid, which is very viscous, is flowing through any pipeline, that time with respect to temperature, it changes with the periodically with the viscosity. So that time we need to add the correction factor, which is 5e is equal to mu upon mu w raised to 0.14. Now this factor is added to the final equation for the laminar flow heat transfer. So I told you basically there are three types: laminar flow, turbulent flow, and transitional flow, where the heat transfer in laminar flow already we have been finished, and the heat transfer in transitional flow is to be seen. Thank you. So this is a correction factor 5e is equal to mu upon mu w raised to 0.14, where mu is the bulk viscosity, mu w is the viscosity at the wall. Now it is very clear thing that whenever a hot or cold fluid is passing around the tube, that time due to heating or cooling, the viscosity is going to change. As I said earlier, the viscosity is very sensitive to the heat temperature. So accordingly, as temperature increases, the viscosity decreases, and thus the rate of heat transfer is also going to change. So this mu upon mu w raised to 0.14, this correction factor is added in the final equation for the laminar flow heat transfer. Here again, Nusselt number is can be rewritten as 2 time m dot cp upon kl raised to 1 upon 3 into mu upon mu w raised to 0.14, which can be said as 2 time Grease number raised to 1 upon 3 and 5. So as I said, the heat transfer is very vast as per the cases differs. In case of laminar flow, transitional flow, turbulent flow, there are various cases. So the next point would be the heat transfer to non-Newtonian liquids in laminar flow. Now, as I said, as per the rheological behavior concern, the line passing through the origin, where the x-axis is shear stress and y-axis is shear strain. So the line passing through the origin is Newtonian fluid, and the remaining all behaviors like fluoroplastic, Bingham plastic, dilatant. Now, especially for this equation, the Nusselt number can be calculated by using equation number 12.26. We have been seen it in last lecture. I am just taking the review. Now similarly, the dimensionless analysis method, empirical equations. So this is the theoretical part. I would like to appeal you just go through this theory and do remember the things which are very important in point of the YY as well as the your exam concern. So now again, effect of tube length. So I told you there are some certain parameters where we need to decide whether the tube length should be short or long. So depending upon the process situation and the space availability at the plant, we need to decide. That is our role. Now generally near the tube entrance where the temperature gradients are still forming, generally the thermal contact in between shell side fluid and tube side fluid is coming at the tube wall, where the local coefficient Hx is greater than H infinity for the fully developed fluid. Now this equation also can be written as, which is shown in 12.35, where Hi upon H infinity. I told you Hi is nothing but inner side heat transfer coefficient, isn't it? Inner side heat transfer coefficient. Now by just using mathematics and by taking the limits Hx to H infinity, x to infinity, the relation between Hi and H infinity can be written as 12 as per the equation number 12.35. Now again, The average value of HI in turbulent flow is very essential. See, as turbulence increases, the heat transfer rate of heat transfer increases. So we need to find out the average value of the HI in case of turbulent flow. Now, with respect to the change in uh, viscosity, mu upon mu w is equal to 1, we can find out the equation HI is equal to 0.023 g raised to point at that is Grignard number. G is k upon k raised to 2 by 3, Cp raised to 1 upon 3 upon d raised to 0.2, mu raised to 0.47. So this equation can be used for the average heat transfer coefficient in turbulent flow. So similarly, the estimation of wall temperature at TW. Now, as we are aware about the TW is nothing but the wall temperature. To evaluate mu W, the viscosity of the fluid at wall, the temperature TW must be found. That estimation of TW requires iterative calculations, which are based upon the resistance equation already we have seen. Now, by using the equation number 12.38, where delta Ti, that is the temperature gradient at inner side, can be written as dO upon di Hi upon 1 upon UO delta T. Now, by substituting 1 upon UO from the equation number 11.30 in our previous chapter we have been seen, and neglecting the wall resistance, we can write delta Ti is equal to 1 upon Hi upon 1 upon Hi plus di dOHO delta T. So this equation is simply, we can say the physical significance would be the delta Ti is equal to inside resistance upon overall resistance into delta T. So as per the heating concern, Tw is equal to T plus delta Ti, where the delta Ti is to be added in case of heating, where in case of cooling, delta Ti is to be deducted from the temperature. If the first approximation is not sufficiently accurate, a second calculation of Tw based upon the results of the first can be made, unless the factor del phi v, that is the viscosity correction factor, is quite different from unity. So similarly, we need to go through all various cases like laminar flow. Already we have been finished with laminar flow. Transitional flow, that is a flow in between laminar and turbulent, and turbulent flow. So I would like to appeal you go through all these equations as per the these cases concerned. Once it is theoretical part, easily you can understand, and here as per the important point of view concern, I would like to appeal you effect of roughness, heat transfer at high velocities, then analogy equations are also very important, where the numerical sums can be asked. Now AD diffusivity already we have been seen in our fluid mechanics, that is Qt upon A, that equation 12.45. Here AD diffusivity is also important for calculation of rate of heat transfer. Then significance of the Prandtl number, AD diffusivity. So this is the theoretical part. I would like to appeal you to go through it. Now the analogy, there are couple of type of analogies, where the first is Reynolds analogy and another is Colburn analogy. So analogy means the similar terms. Here I told you Prandtl number is nothing but it is the ratio of nu, that is the viscosity, kinematic viscosity upon thermal diffusivity. Sorry. Now by taking the ratio we are getting the Prandtl number, and we are just going to equate it, we are going to correlate with the Prandtl number and the Standard number, where H upon Cp into G into NPR is equal to F upon 2, where F is the friction factor. You might remember about the fanning friction factor in our fluid mechanics in chapter I think second chapter in section second, where we have been seen F is nothing but friction factor. Now this is the usual form of the analog equation. H upon CPG is equal to Stanton number is equal to F upon 2. So this can be asked for Viva as well as the theory also. So generally in question number 4, question number 4, the question can be asked to write a short note on the Colburn analogy and Reynolds analogy for 6 marks. So as per your case concern, it might be asked for 4 or 5 marks. So another is the Colburn analogy, where the J factor is also considered. This is over the range of the actually the range of the Renault number is differs point to point, and it differs the rate of heat transfer point to point. Now, as per the case of Renault number, which is having in between 5,000 to 20,000, the friction factor for the smooth pipe, or 20,000 or 2 lakh, the friction factor for smooth pipe is adequately given by the another analogous equation, that is F is equal to 0.046 d into g upon mu raised to minus 0.2. Now if we will compare these equations, then easily we can find J's factor, that H upon Cp into G, Prandtl number is to 2 upon 3 into the product of or the ratio of mu w upon mu, that is the kinetic viscosity correction factor, this is equal to JH is equal to F upon 2. Now this equation is statement of the Colburn analogy in between, which gives the relationship in between heat transfer and the fluid friction. So friction and heat transfer both are the analogous terms. So this Colburn analogy is used for finding out the relationship in between friction and the whatever the heat transfer rate. So accordingly, these couple of equations are very important. I would like to appeal you, go through it: transition region, turbulent region, and again the laminar transitional turbulent is now the another case is the transfer of heat transfer to liquid metal. I told you many times the mercury plays very important role. Generally mercury is used in nuclear reactors, where it is having the ability to sustain the heat. So transfer to liquid metal is also important part, where which is asked for the 4 to 5 marks, where you need to discuss about the Nusselt number equation along with the empirical constants alpha, beta, and the gamma. These are the function of geometry, and also with respect to Piclet number, you can easily elaborate this relationship. Now you might came across the dimensions number like Renault number, Piclet number, Grids number, and Nusselt number are correlated in this chapter. So each and every number has its own significance in case of rate of heat transfer. So you need to keep in mind which number is very important for the further with respective point of view. So accordingly, same point is going to repeat again. It is just for heating and cooling of liquid fluid in forced convection of for outside tubes. So this graph I think we have been discussed. So this is the natural convection. So natural convection already you know, it is nothing but the mode of heat transfer where the heat is transferred from high point to low temperature, high temperature to low temperature, due to density difference with actual migration of the fluid particle. So generally everywhere we can see the convection. So if I will take a cup of tea, I will keep as it is, then it will be the natural convection. But if I will pour it into the saucer and I will just blow the air along with my mouth, then that will be the example of the forced convection. So industry cannot wait for the natural convection. Always keep one thing in mind, that to increase the rate of heat transfer, we have to have the forced convection. So accordingly, These are the graphs which are showing the distance from plate surface versus local temperature. So go to this graph and those equations. Then furthermore the equations are there, some examples are also solved. So this is all about this chapter. Now in next lecture I would start with the heat transfer to fluid with phase change. Thank you.